Okay, so today we're going to do the third word problem from the fourth nuclear worksheet, which involves a radioactive substance, they don't tell you what, which has a half-life of 30 days. The first part asks you to calculate the radioactive disintegration constant, lambda. The second part is the average life, which we just call half pi because we don't know what it is. C is the time taken for 3/4 of the original number of atoms to disintegrate, and D is the time for 1/8 of the original number of atoms to remain unchanged. Kind of complex wording, but we'll get to that when we get there. The first part is to calculate the radioactive disintegration constant. Now, there's an expression for how much radioactive material is left after a certain amount of time, and that's 2 raised to the negative time over the half-life. And we already know the half-life is 30. So we'll just substitute that in. And this is equal to another equation which has the radioactive disintegration constant, lambda, in it, which is e raised to the negative lambda t. Now, to solve for lambda to find the disintegration constant, we take the natural logarithm of both sides and get that negative t over 30, natural logarithm of 2, is equal to lambda t, negative lambda t, because the natural logarithm of e is just 1. Now, we can cancel out both the negative sign and the t from both sides of the equation and get that 1/30th of the natural logarithm of 2 is equal to the disintegration constant. Now, on to part B, which is the average life of a particle. This is not the half-life. Then that's important. If you take any one particle, it's the average time before it decays, not the time it takes for half of the mass of a substance to decay. Now, there's another equation that will provide to you how much of the original substance is left. Only this one uses the constant as the average life of the particle. So we have our e to the negative t over half pi, which is the average life of the particle. Now that's the equation of how much is left after t time, is equal to e raised to the negative 693t over the half-life, or 30. This is just another one of the about 6 equations that provides to you the amount left after a certain amount of time. So again, we take the natural logarithm, canceling e from both sides. So negative t over the average life of the particle is equal to negative 0.693 t over 30. Negative and t cancels again, and we take the reciprocal of both sides of the equation to get that the average lifetime of the particle is 30 divided by 0.639, or 43.29. Okay, now we're going to move on to C, where we calculate the amount of time taken for 3/4 of the original number of atoms or mass to disintegrate. Now we finally get to apply one of these equations. We're going to use the e raised to the negative t divided by the average lifetime, just because we recently calculated that. Now, that would be equal to 1/4, because if you think about it, if 3/4 has decayed, that meant if you started with 100%, 25% would be left. Therefore, 3/4, or therefore 1/4. Now, we take the natural logarithm again, and we get the natural logarithm of 1/4 is equal to negative t over the average lifetime. We can plug in the average lifetime we found earlier of 43.29. And get that t is equal to 60.01, or 60, just 60 works. Now, finally D, the one with awkward wording. The time taken for 1/8 of the original number of atoms to remain unchanged. This just means that 7/8 has decayed. So instead of the equation being equal to 1/4, now it's equal to 1/8. So 1/8 is equal to e to the negative t over half pi over the average lifetime. So we take the natural logarithm again and get natural logarithm of 1/8 is equal to negative t over half-life. Solving and plugging in for our value of half pi, we get that t is equal to 90.02 or 90. We probably took out the average of the value of half pi to one too many decimal places. The problem was probably expecting 3 decimals at 43.2 or 43.3 instead of 43.29, and therefore our answers were slightly off. The correct answers for C and D are 60 and 90. Okay, that's the problem.